Hello, let's start this. Let's try to find the area of the ellipse using Green's function, right? Here it's x square by a square plus y square by b square equal to 1, where a comma b are positive numbers. Fine. So uh, we know the Green's theorem's formula, right? The Green's theorem, right? Here Green's theorem for a region bounded by a positively oriented curve C. This will be P dx plus Q dy is double integral over this region R dou Q by dou x minus dou P by dou y into dx dy. Right? This is the Green's theorem formula. Right? Just nothing but if there is some closed curve, right? If this is some closed curve, this is the region R, and P comma X are the functions of X and Y, right? And they are continuous partial differential derivatives there, then this satisfies this relation. Fine. Now we need to find the area of an ellipse using this Green's theorem. Fine. As you can see in the right hand side here, you can see this is dx dy, right? If you want to find the area of area, you need to integrate dx dy, right? So you need to make sure that dx by dy minus dou p by dou y is some constant, so that it will come out of the integral. Then it will be double integral of dx dy over the whole region, right? So let's try to take uh, q and p, the functions of x and y, such that they becomes constant. So let's consider the easiest way. As you can see, px comma y, right? As you can see, there is dou p by dou y, right? If px comma y is minus y, right, then it will be minus 1, minus of minus 1 you will get plus 1. If q of x comma y is x, then dou p by dou x is 1. So now let's try to calculate this. Dou q by dou x minus dou p by dou y is 1 minus of minus 1, which is 2. Fine. Now this becomes over this region dou q by dou x minus dou p by dou y dx dy is, now this becomes the region R into 2 comes out, then dx dy is equal to integral along closed curve p dx, right? P dx is, here it is, p is minus 5 dx plus q is x dy. Fine. As you can now see here, it's dx dy is area, right, over the region R. Now to need to calculate the area of the ellipse, we need to know the area, the region over R must be ellipse. So let's try to parameterize let's parameterize the ellipse, right? For ellipse, x equal to a cos theta, y is b sin theta, right? I mean, any arbitrary point on the ellipse can be defined as x equal to a cos theta, y equal to b sin theta. As you can substitute there, it will be x square y square plus y square by b square will be 1, right? And here theta is 0 less than or equal to 2 pi, right? Then you can calculate dx. This will be minus a sin theta d theta, and dy is b cos theta d theta, right? Finally, let's try to calculate this first. So this will be closed integral x dy minus y dx. Fine. Then this is integral 0 to 2 pi, as it is a closed curve, right? Then this is a cos theta, x is a cos theta, dy is b cos theta, b cos theta d theta minus y is b sin theta, then dx is plus a sin theta d theta. So let's try to write it in this form here. You can bring this eb out, and this will be integral 0 to 2 pi cos squared theta plus sin squared theta d theta, right? Then this is ab into this value gets 1, then this will be d theta. Theta ranges from 2 to 0 pi, 0 to 2 pi, then this value is 2 pi into ab. Fine. Now let's bring this here. Let's substitute this formula here. 2 into dx dy here are, right? This region is ellipse because we have parameterized x and y as ellipse. So this is equal to 2 pi ab. Fine. This 2 will get cancelled, right? Then this is area, right? So finally area of the ellipse is pi ab. Fine. Now, I mean, you can just calculate using polar coordinates too. Let's solve that. Right, using polar coordinates. Let's assume this as x-axis, this is as y-axis, and you can calculate, right, this the first in the first quadrant, right? You can calculate this first quadrant area, and you can multiply with the factor of 4, then you will get the area of an ellipse. Fine. Then you can write area of an ellipse as 4 times of integral f of x into dx, right? Here f of x will be y dx, right? Dx value ranges from 0 to a. Fine. Now let's proceed. As we are using the polar coordinates, here x will be a cos theta and y equal to b sin theta, as we have done previously. Here dx equal to minus a sin theta d theta, right? Dy equal to b cos theta d theta. Then a is 4 times of integral 0 to pi by 2. Sorry, we need to calculate the integration limit side. Fine. We have taken if x equal to 0, then if x equal to 0, then cos theta is pi by 2, right? As cos pi by 2 is 0. If x equal to a, if x equal to a here, then it will be a by is 1, then cos theta will be 0. Fine. Then a is 4 times of pi by 2 to 0, y is b sin theta, and dx is minus of a sin theta into d then. Fine. This convention, because of the negative symbol here, the integration limits will get interchanged, and you can keep ab out of the integral as their constants. This will be 4ab integral 0 to pi by 2, right, sine square theta d theta. Fine. Then a equal to 4ab integral 0 to pi by 2. Sin square theta can be written as 1 minus cos 2 theta by 2 2 theta, right? So let's try to solve this. 4ab by 2, right? You can just do 4ab by 2 into integral d theta will be theta, and pi by 2 minus 0 is pi by 2, minus integral of cos 2 theta. Integral of cos 2 theta is sin 2 theta, right? Sin 2 theta by 2, then integral 0 to pi by 2. Fine. This is 2ab into pi by 2 minus half into when theta is pi by 2, it will be sin 2 into pi by 2. 2 will get cancelled, sin pi, right? Let's write it here so that it will be, you can understand properly. Sin pi, right? Sin pi is 0. When theta is 0, it's 0. That is, then this is 2ab into pi by 2. 2 will get cancelled. Then this is pi ab. Fine. That is, area of an ellipse is pi ab. So it's proved using polar coordinates.